energy stored in a capacitor. Energy, when we give the charges to the capacitor plates, the energy will be stored. That is, the energy will be stored as electric field, because when we give the charges to one of the plate, let us say one plate is given the positive charges and the other plate is given the negative charges. In that case, what happens is the two charges, the two set of charges will be staying there on the plates due to the electric field which is attracting the charges, and they are keeping that charges in their position. Now what we have to do is here is, we know that we have a capacitor and we know that one of the plate is going to be positively charged and the other plate is going to be negatively charged. Now initially when we have a capacitor, it will be uncharged. There will be no charge present between the plates, or there will be no charge on those plates. When we start charging it, that means when we are giving the charges, one plate becomes positively charged, one plate becomes negatively charged. So what we are doing in process is, we are removing one type of charge from one plate and we are adding the other type of charge to the other plate. What we can say here is, this plate was initially neutral, this plate was also initially neutral. What we did was, we removed all the positive charge from this plate and we gave it to this plate, and we removed the negative charge present on this plate and we gave it to this plate. Now what happens is, these charges are going to stay there for a very long period of time, and that is the capacitance. That is, the charges are going to be stored in the plates. Now let us say in the initial situation there was some charge Q dash and there was same amount of negative charge on the other plate. I am going to call it as Q dash. Now why I am going to take it as Q dash, why not Q and minus Q? Because that situation is going to come at the end when I fully charge my capacitor plates. It is an intermediate stage. It is the transition phase when the capacitor plates are getting charged. Whereas in the final situation, what I am going to get is a fully charged capacitor with one plate which consists of only the positive charges and the other plate contains only the negative charges. And when this situation arrives, what we are going to have is an electric field will be going to be present in between the plates. And as we know, the electric field is always directed from the positive side to the negative side. Now this is the intermediate phase. What we are trying to do here is, we are taking a small charge delta Q, or as a matter of fact, let's take it as just simple letter dq. That small amount of charge, it is a positive charge, it is taken from the negative plate and it is being given to the positive plate. When this charge is going to be removed from this negative plate, this negative plate becomes even more negative, and this positive plate, which was already having some positive charge, when this small charge dq arrives here, it is going to become even more positive. We are removing the positive charges from this negative plate and we are giving it to the positive plate. Let's, for simplicity, let's keep the consistency. This is plus Q dash, this is minus Q dash, and this is dq dash, which is a small positive charge which is arriving from the negative plate and it is moving towards the positive plate. We are moving a small positive charge against the field, because as soon as this plate acquires some amount of positive charge, this plate is going to repel this dq dash, that small charge. At the same time, when this plate has become negative, what this plate does is, it is going to attract this dq dash, because this is a positive charge, it will be repelled by the positive plate and it will be attracted by the negative plate. So field is from positive side to the negative side. When the field is in this direction, what we are doing is we are trying to move this small charge against the field. So when we are moving that charge against the field, that means we are doing that work on this small amount of charge. So what we are doing, we are moving it against the field. Same work will be stored in this capacitor when it is getting fully charged to the final state. So what we have here is, it is a transition phase. The capacitor is not completely empty and also the capacitor is not completely filled with charges. It is in the intermediate phase. So what we have here is the transition phase. The charge dq, it is in the small amounts, it is getting transferred from the negative plate towards the positive plate. So what we are doing here is, we are removing the positive charges from the negative plate and we are giving it to the positive plate. So that is what is happening in this diagram. For simplicity, let's take the numbers as this is plate 1, this is plate 2. In the final state also, we are going to have the plate 1 and plate 2. What will be the potential across the plates when that small charge dq dash is moving between the plates? So when we have this charge, we also have the capacitance. When we have that capacitance, the potential, the general equation, or I can just write the equation for capacitance, C is equal to Q divided by V. That is the general equation for capacitance. I want to extract the potential of this capacitor from this equation. So what it is going to be? It will be V is equal to Q divided by C. But what kind of Q do I have on each plate? It is not Q, it is just Q dash. And at the same time, because this is not the final potential, it is the transition potential, I am going to take this V as V dash. So intermediate potential V dash is equal to Q dash divided by C. So that is my current situation of potential on this capacitor. Now what we are doing here is, we are making that small charge dq dash to move against the field. So when we are moving that charge against the field, so when we are moving that, what we are doing? We are doing the work. What kind of work it will be? We know that work is W. W is given by, it will be V into dq dash. And what is this V? It is V dash. And because we are doing a small work, I am going to take it as dW. So what we have done here is, we have moved a small charge dq dash from the negative plate towards the positive plate, and in doing that we have done a small amount of work, and that work is going to be given by V dash into dq dash. Now I have the equation for potential from this one. I can substitute this equation for V dash into that equation. So this is going to become, what I have here is Q dash divided by C into dq. What is this? dq dash. What is this? This is small amount of work which we are doing to move this small charge against the field. Now if I want to do the complete work, now what will be the complete work? The complete work will be, all the positive charges which are present on this negative plate should be taken and they should be given to the positive plate. So what we have here is, we are going to do the complete work. So what will be W? W will be integration of dW. So integration of dW gives us W, that is the complete work done when we are moving the whole charges from the negative plate towards the positive plate. Now dW is given by this equation. What is that? It is Q dash divided by C into dq dash. The initial situation, when there was no charging of capacitor, what was the total charge on each plate? It was 0. When the capacitor was initially uncharged, the charge present on positive plate will be 0. the charge present on the negative plate will also be 0. So initial condition is it is 0. So I'm going to take the lower limit as 0. Now what about the upper limit? What is the situation at the end? This diagram represents the situation at the end. The capacitor plate, the positive plate of the capacitor is plate 1. It is going to be completely charged to a value of plus Q, and the negative plate or the plate 2 is going to be completely charged to a value of minus Q. So each plate has a value of a quantity of Q amount of charge on each plate. Positive will have plus Q, negative will have minus Q. Now this is integration, and we are going to integrate with respect to one variable. Now what is the quantity which is changing in these two diagrams? It is the charge, that is dq, which is moving from negative plate to the positive plate. So we are going to do the integration with respect to that q dash. So if the integration is happening with respect to q dash, that means c is a constant, it is going to go outside the integration. So w will be equal to 1 by c integration of between the limits 0 to q, it will be integration of q dash into dq dash. So in differentiation the power will be reduced and the initial power will come as a multiplier, whereas in integration the power is going to increase and the same is going to be becoming a divider. So now what I am going to do, I am going to do the integration. What is the power here? It is 1. Because if nothing is there, the power is going to be assumed to be 1. So my value of this yum is 1 in this equation. What it should happen? 1 plus 1. That means the power should become 2. So what I have outside the bracket? It will be 1 by c integration of q with respect to dq. It is going to give me q dash square between the limits 0 to q. Here I had x, I'll just take it as one more step. Let's take yum is equal to 1. So it is going to be x dx, and this is going to give me x square divided by 2. So using this equation, what I have got is I had q dash, I got q square. So power is increased and the same power will appear in the denominator. So it is going to be q dash square divided by 2. So that is going to be the result of my integration. Now applying the limits. How the limits are going to be applied? It is always the final situation minus the initial situation. In this case, the final charge minus the initial charge. So this 2 is a constant. I can take it out with this c. So it is going to become 1 by 2c. And in the bracket, what I am going to get, it is the upper limit. That is going to be q square minus lower limit, it is 0 square. And that completes my derivation. W will be equal to, this q square is going to come out, it is going to become q square divided by 2c, and whatever the work we have done, the same work will be stored in the form of potential energy. So this equation becomes u is equal to q square divided by 2c. It is the work done on the body. So whatever the work will be done on the body or on the system, that same work will be stored in the form of potential energy. So what we did here, we moved the charges between the plates against the field. The field was going from left to right. We were moving the charges from right to left. So in moving those charges, we are going to do some work. And that work is going to be stored in the form of potential energy. Now starting with, when this plate is having some amount of positive charge, this plate is having some amount of negative charge, there will be a potential difference developed between the plates, and that potential is given by this equation, that is V dash equals Q dash by C, because this is a derivative of this equation, that C is equal to Q by V. Then what we are doing here, we are moving a small amount of charge, that was dq dash, from the negative plate towards the positive plate, and we are doing it against the field, so we are doing the work. So we get this equation dw, because it is a small work, small charge, we are going to get a small work dW equals V dash into D into Q dash. I can write this equation, and this equation V dash, we already have that value is Q dash by C. So when I substitute that, I get this equation dW equal to Q dash by C into dQ. And this was the situation when we were moving only a small amount of charge. But when we try to move the whole charge, or when we are completing the whole movement of the charge, we are going to get the complete work, which will be the integration of that small work. Substituting this equation here, we are going to get integration of Q dash by C into dQ between the limits 0 to Q. What is 0? The initial situation when the plates were totally uncharged. And what is Q? It is the final situation where the plates are fully charged. So we are going to have the integration between the limits 0 to Q, and the equation remains Q dash by C into dQ dash. This C is a constant with respect to this dQ, so it is going to move out of integration. It will be 1 by C outside the integration. Integration again between the limits Q into dQ dash. And according to this logic, we are going to get integration of x into dx is going to give us x square by 2. Same integration applies to this Q dash. It is going to get Q dash square divided by 2. 2 is constant, it comes out. Applying the limits, upper limit minus the lower limit. Q dash will be once substituted with upper limit, and once it will be substituted with lower limit. Whatever the way it is given, it is going to be substituted in that way. It is going to be square. So we are going to get a Q square, that is the upper limit. Then we are going to get a 0 square, that is the lower limit. And simplifying this equation, this Q square will be multiplied by this one. We are going to get the total work as Q square by 2C, and that is going to be my potential energy, or the energy stored in the capacitor. U is equal to Q square by 2C. This is my equation of capacitance. Now, this Q square, we also have Q is equal to CV. How it is coming? From this equation. If I cross multiply this V to this C, Q becomes equal to CV. That is there. If I substitute this equation in the place of this Q square, what is going to happen? I have got U on the left hand side. Q square means it is going to become CV whole square divided by 2C. So 1C and this C square, I will just open the bracket. This is going to become C square V square divided by 2C. This C and this square cancels out. What we are left with is half C V square. And be careful, this is a capital V which represents the potential. We are not talking of velocity here. We are talking of potential. Potential is represented by capital V, whereas small letter v represents velocity. Be careful with that. So this is a capital V, so it is half CV square. It is half CV square. So this is one equation of energy stored in capacitor. This is the second equation in the energy stored in a capacitor. Alternatively, we also have C is equal to Q divided by V. So if I substitute this as this, what is going to happen? U is equal to half. C can be replaced by Q divided by V, and that is going to be V square, and we know this V and this V square will cancel out. It will be half Q V, and that is going to be potential energy. So this is my third equation. Energy density. Some books have referred it as energy density. Some books are referring it as energy density of capacitor. Some books are referring it as energy density of electric field. So it is just the energy density, and your NCERT book doesn't even define it as a term. It is just given as a subtopic inside that energy of a capacitor. So what do we have here is, When we have capacitance, the value of capacitance is given by epsilon naught A divided by D. This is the equation of parallel plate capacitor. This we had seen at the end of the derivation of capacitance. Now, if I have a surface, what do I have? If I have a plate, there will be charge distributed all over the area. So when I have that charge distributed all over the area, that means there is a surface charge density. Then, so if sigma is the surface charge density, I can extract two things. First one is Q is equal to sigma into A, because what is sigma? Sigma is Q divided by A. That is the charge per unit area. This is one thing that we can associate with that sigma. What is the other thing which we can associate with the sigma that we have mostly used? E is equal to sigma divided by epsilon naught. We have seen these two equations which are in relation with respect to this sigma. One is talking about the charge, one is talking about the electric field. Now, what do I have for the electric field is, I can rearrange this equation. I am going to get sigma is equal to E into, or I can take it as epsilon naught into E, just a cross multiplication, and using this equation for sigma into this equation. So what is going to become? It is going to be Q is equal to epsilon naught E into A. So now I have the charge in terms of electric field. Now, what is my energy? Energy, I have got those three equations. I will take the first one, and that is because that is going to be directly associated with U. So it's like Q. So U is equal to Q square divided by 2C. Now, I need a Q in the numerator, which is already present here. I need a C in the denominator, which is here. So I am going to substitute these two values of Q and C into this equation. That equation, in a few steps, I am going to get the energy density. So what I am going to get here is Q is epsilon naught E into A, and that is going to be whole squared divided by 2. C is these many terms. It is epsilon naught A divided by D. Now, just for your understanding, A stands for area of the plates and D stands for the separation between the plates. So that is what we have. Now, on simplification of this equation, just I am going to go step by step. Opening the bracket, it is going to become epsilon naught square E square A square, and this D comes up, it is going to be D at the end, whole divided by, it will be 2 times of epsilon naught A. So now observe the things that cancel out. So we have this epsilon naught goes out, one square term is going to go out, area is single, area is squared in the numerator, it is going to go out. So what is left here is epsilon, 1 is gone. First of all, I will take care of this 1 by 2. That is first thing. Then 1 epsilon is gone, 1 epsilon is left. Epsilon naught is there. Then what is left? Next is E square. That is the electric field square. A, it was squared, 1 is gone, 1A is left. And at the end, there is a D. Now, if you know A was the area of the plate and D was the separation between the plates, and these two terms together, they are going to be the volume present between the plates. So what is volume? It is the product of area and the separation. Area is a 2-dimensional quantity, separation gives the 3rd dimension. So this entire space between the plates, it is going to give us the volume of the capacitor, or the volume or the region in which that electric field is going to spread, and that electric field is going to be completely filling up the space between the two plates, and that is going to be given by that volume, which is the product of area and the distance of separation between the plates. Now, what we were looking for? We were looking for energy density, energy per unit volume. So, do I have a volume term here? Yes. So, if I want that volume term per unit volume, then it is going to be, I am going to take it as the small letter u, and that will be equal to capital U divided by volume, that is going to be represented by AD. What is that AD? AD is the volume of space present between the plates. So when I divide this capital U by this AD term in this equation of U will cancel out. What is going to be left with me? It is only half epsilon naught E square. This equation represents the energy density of a capacitor or energy density of electric field. U square by 2C. This was the energy equation which we derived few minutes ago. An extension of that one gives us the energy density or the energy per unit volume of a capacitor or energy per unit volume of electric field enclosed between the two plates of a capacitor.